today we're going to talk about how we're adding factuality as a signal to our text and search arenas. And we're going to talk about how we do this, some of the math behind it, and most importantly, why we're doing this. So I guess, Tijana, why don't you talk about what exactly we're adding and why?
Yeah, so far our leaderboards have primarily been based on measuring human preference. And one thing that we've observed is that human preference and factuality are actually two complementary signals, and we want to incorporate both in our evaluations. In particular, some responses might not require fact-checking at all. For example, someone might have a creative writing task, and the model response might not produce any claims that are worth fact-checking. And so in those cases, we do care about human preference, but we don't necessarily care about factuality. At the same time, for some other responses, the models do produce claims, and we do want to make sure that those claims are factual, but manually verifying those claims is very time-consuming, it's very slow, it's nearly impossible, and so we shouldn't really expect that our human preference signals reflect factuality as well.
Yeah, and I think we've tried to attack this problem before with style control, right? And with style control, we try to measure style elements like markdown, length, and so forth, and we can control for them and any biases they may induce in a human vote. The purpose of this was to protect against a response that looks really good but is actually filled with tons of inaccuracies or just straight up being wrong, and maybe the length makes it more preferred by humans or something of this sort. Factuality largely attacks a similar problem, except it targets the issue directly, which is, hey, is this response filled with a bunch of information that's wrong? And we're just measuring that and penalizing that to make it impossible for a model to be top on a leaderboard while producing lots of inaccurate information for our users.
Yeah, exactly. And of course, we shouldn't necessarily punish style, right? Because style control so far has largely penalized some stylistic features like length, markdown, and so on. But in many cases, style is actually really essential in communicating effectively. And so, all else equal, like having two models that are equally factual, we actually want to reward style. And if human preference rewards style, that should be okay.
Yeah, that's a unique thing we can measure on our platform, which is the part where models communicate with people, right? So I think it's definitely important that we keep that in. I guess we should go into the math itself.
Yeah, let's get into the math. To give a little bit of context, it's useful to just review what we've been doing so far, how we've been constructing leaderboards based on human preference, and then we'll show how we've extended this methodology to also incorporate factuality. So far, we would collect data that is of the form A, B, Y, H, where A and B are two models that we sample on the platform that are anonymous. YH is a label that indicates which model is the winner. So this would be a number that we encode as 0, 0.5, or 1, where 0 and 1 indicate that model A or B win respectively, and 0.5 indicates a tie. And then what we would do is we would construct an objective that is the average loss over all our battles. So here this loss L is the so-called Bradley-Terry loss. And here N is the total number of battles we have on the platform. So we aggregate all our data that consists of model identities and labels of which model won, and we construct a loss function. And then the scores that you see on our leaderboard website are given by optimizing this loss function and rescaling these numbers appropriately so that you see these numbers that are like on the ELO scale. Now, what we do with factuality is pretty similar. So we, again, have model battles, and we get a label YF. And in a few minutes, Evan will tell you how we obtain these labels exactly. So these labels are, again, numbers in 0, 1. In particular, to construct this data, we randomly subsample some fraction of the battles that happen on our platform, and then we fact check the two responses individually. And then after we fact check the two individual responses, we obtain this label. And so now, once we have this data, and it looks pretty analogous to the data that we had previously, we can construct a similar kind of objective. So now the number of battles could be different because we don't fact check all the battles. And so this is the loss function that we construct. And now, once we have these two losses, we just construct a convex combination of these two losses. So in particular, we have this composite objective where we add a weight for the human preference part of the objective, and then a weight for the factuality part of the objective. We set these weights so that they add up to 1. And finally, we compute our final scores by minimizing this composite objective. And so, so again, for a model to perform well according to this composite objective, it has to perform well both in terms of human preference and in terms of factuality, because the loss that we're optimizing combines those two into a single objective.
And so previously, this theta is the strength parameter for each model. It's only dependent on the human preference. Yeah. And then conversely here, it's only dependent on the factuality. And so here then they're combined, and specifically they're combined with these weights. So which we can control, and we can look at, hey, like, if we weight factuality at 25%, what are those scores like, such that the new strength parameters we're learning are weighted in that way, right?
Yeah, and if you actually look at the plot, if you compare the solution that you would get by just optimizing human preference and the solution that you would get by just optimizing factuality, you see a very different ranking. And so we can indeed see that human preference and factuality are measuring complementary signals.
Yeah. And I guess we should talk about
tell us
YF, right?
Yeah, tell us about YF.
Yeah, so I actually want to start backwards and say that we are given some battle, right? And so battle from a model, and of course each battle has two sides. So let's just assume this is one side. So from the battle, we're gonna pull out, we're gonna extract claims A and claims B, where claims A is all the claims made by model on the model inside A, and claims B is all the claims made by model inside B. There can be 0 or more claims, of course. And so for each claim, we can run this verifier that we have that takes in a single claim and produces a 0-1 score, right? There's a probability that this claim is true. And then for a given side, then we can get what we will define as the average factuality probability, which is simply this. So we're just looking at the average factuality score for all the claims. So if you produce lots of claims and they are all correct, then you'll have an average score of 1. If half of them are correct and half of them are probably wrong, then you're going to get 0.5 and anywhere in between. Okay, and then we look at we have to define a 0-1 objective, as you said here. And so what we do is we're going to define. I'll switch colors here. We'll define YF is equal to a sigmoid, which compresses it of the average probability of being correct in side A minus the average probability correct on the other side, divided some temperature just to normalize everything so it looks clean on the leaderboard, and that's YF. That's it.
Yeah, and I guess at the beginning we were saying that not all responses actually require fact-checking. So can you tell us a little bit about, how we ensure that models that are not producing any facts worth fact-checking, how we ensure that those models don't get penalized?
Yeah, so what we're looking for is a system that doesn't penalize abstinence, right? So if I am well calibrated in my knowledge, I just won't say things if I don't think they're true. I should, in fact, only say things when I'm reasonably confident that they're true. And so what that means is a model that produces no claims in the response can't lose a factuality battle. It can, if the other model also emits no claims, that's, there's no factuality here. We don't emit anything. If the other model produces true claims, it's also good. That's a tie. If the model produces false claims, the model that didn't produce any claims at all will win. Because we don't want to double penalize. Presumably, if a user talks to a model and the model's like, hey, I just don't know anything, the user would be like, okay, I don't like this response. And we wouldn't want to double penalize them on factuality as well, just for abstaining from giving false information, right? So essentially, it'll just have like CICB. We're looking for models that are calibrated in what they add to their set of claims, which you would hope most of them are high quality. And we definitely want to penalize models that are just shooting off claims like nobody's business, and half of them are wrong. And oftentimes the user may not be able to tell because it's subtle and it's everywhere, and nobody has time to fact check 100 claims in some sort of like really long response, right?
Yeah. And so, so this tells us how we estimate the scores. This tells us how we get the Ys, the labels that are used for the factuality battles. And now what we do in the end is we put confidence intervals around this estimator. So in particular, if we define theta star to be the population solution of this objective, so this would be the minimizer of the population version of this loss, which is just equal to the expectation of this objective function. Then by leveraging standard tools in M estimation, which is a classical topic in statistical theory, we know that our estimator is asymptotically normal around theta star. So it converges to a normal distribution with a covariance that has an explicit closed form expression. So this covariance has the usual sandwich form. So it has like a Hessian inverse, gradient covariance, Hessian inverse, and all of these matrices have explicit plug-in estimates. So all that is just to say that we know how to compute a sigma hat that converges to the sigma. And then finally, we can just, now we know exactly how to bound the fluctuations of theta hat around theta star. And so we can construct the usual confidence intervals based on the central limit theorem.
Should we prove it here, or should we leave that as an exercise to the reader?
Yeah, that's an exercise for the reader.
Because it's really simple.
Because it's very simple.
It's very simple, yeah.
Exactly. Great. So that's a little bit about our methodology.
Yeah.
And we're launching these leaderboards. Please give feedback on the methodology, on the leaderboards. And we are looking forward to incorporating factuality into our other evaluation products as well. So stay tuned.
Yeah, this will be cool. We want to make sure that models are reliable for everyone, and we want to measure all these details about how these models behave in the real world.
Awesome.
It is A minus B, right?
It depends on, it doesn't matter. If you flip 1 and 0, it doesn't matter. Yeah. I think normally we do A minus B. So 1 is A. I think I said the opposite of what was true, but that doesn't matter.
Yeah, I never understood what the Hessian thing was doing.
Oh, well, that's the B, not the Hessian. Yeah, the Hessian is...
Oh yeah, why is the Hessian?
Anyway, we can write, if you wanted the proof.
Yeah, write the proof.
It's just the Taylor expansion. So you know that
But you can write it wherever now.
So you know that this is 0, an expectation, and so now you're gonna...
Do you need to put an E over it, or no?
So yeah, let's just, this will be like no, there's no E because this is just by definition of theta hat, it optimizes the empirical.
Yeah, okay.
And so
then because L is defined as this, yeah.
Yeah, and then you do you expand around theta star plus, at some point times theta hat minus theta star. And then you do, so then you do like theta hat minus theta star.
Is that guaranteed equal, or is that an approximation technically?
Well, it's true for some point.
Okay.
Yeah. Or you can do it at, It's true for some point between these two. Okay. And so then you can do this, right, times this minus.
I see. So that's where you're getting the inverse.
This is 0, so it doesn't matter. And then you just get this, right, with like a minus. And so, and now basically, now this thing is just an average, right? Mm-hmm. So you apply the CLT directly. Okay. Because it's just like an average of things. So you apply the CLT there, and then this thing is just like this converges to this like population Hessian. And so basically it just like multiplies the covariance in the CLT. So this goes to, right, this will go to normal 0B. And then this is Hessian inverse. So when you apply this all together, it goes to normal 0 H inverse B H inverse. Does that make sense? And then that's how you get it.
Can you explain there to there?
Yeah.
Because I don't see HBH
because
yet.
you need to, so you need to normalize by root n everywhere.
Okay.
Root n.
Okay.
This thing, I'm claiming that this converges to H inverse. So this is, again, an average. And so because it's an average, it, by the law of large numbers, it converges to the population thing. So this converges to H inverse. And I'm saying if you have normal, so like if you have a normal distribution, let's call this something else, like A. You have a variable that's distributed like this, and you multiply it by some matrix M. That is equal in distribution to normal 0, like, I guess it depends on if this is symmetric. Let's just say something like this.
Yeah, it all works out.
Depending on how you have to transpose things.
Is that T or is that plus?
No, this is like a transpose.
Oh, transpose, okay.
Yeah. And so I'm just saying like that's what happens here in this step. So you have H multiplying this thing that converges to normal 0B. You get like exactly the variance of the gradient.
So this
right?
H is getting like that's that one.
That's the
I understand.
And this is the variance of the gradients because the CLT has the variance, right? And so the root n plus this goes to this, and then you just like hit it with an H, and that's it.
You said it was going to be 2 pages.
Well, this is the sketch, but if you want to actually like formalize all this, so I mean,
I guess we didn't talk about any of like the linear combination stuff that you would need here, right?
But the point is like under reasonable assumptions, like for example that m prime and n, like the ratio of m prime and n converges to a constant, stuff like that. Like under all those assumptions, like all of this works out basically.
Yeah, so like basically you don't want like to have like an insane amount of human vote and then like a decreasing amount
you
of
can't
like
have this go
factuality
to
votes over time
exactly.
or something.
And then this is like,
or like God forbid it's like you don't have any factuality votes or vice versa. All of that is like, that's all you're just
exactly, because you have like a common sample size that you're normalizing by. So that means that both of these numbers have to actually be proportional to whatever you're putting here on the left-hand side.
I see. That makes sense. That makes sense.
That's the,
Cool. Are these exact?
What do you mean exact?
I don't know. Are they exact?
I don't know what that means. All of this is asymptotic. So none of this.
Oh, okay. It's all